My name is Putri Nur Aqilah binti Megat Mustafa, metric number 2020495354 from RAS 20348. In this video, I will explain about Schmidt's law. Schmidt's law is defined as a relationship between shear stress and the orientation of the slip system that can be defined with this equation. So, how can we define this equation? The angle alpha describes as the angle between external tensor force and surface normal of the slip plane. The orientation of the slip direction is analogously defined as angle beta between the force axis and the slip direction. Note that the both angles are only independent within a certain range. First, the external force is broken into a component acting in a slip direction. This is done via the cosine of the angle beta. The quotient of shear force at slip plane surface alpha yields the shear stress relevant for the sliding process torque. Thus, in addition to the force dependent to the angle beta, the dependence of the slip plane surface on the angle alpha must be known. If the cross-sectional area of the sample is denoted by A naught, then the slip plane area A is given by the angle alpha as follows. Then, the shear stress torque in slip direction of an arbitrarily inclined slip plane is calculated as follows. The expression F naught over A naught corresponds to the externally applied normal stress. In this way, the following relationship between the externally applied normal stress and the shear stress induced in a slip system torque can finally be established.
So, before we go into explain about Schmidt's law for the electric current induced deformation, let's take a look on an example of calculation of resolved shear stress. Let's take a look on this figure. Let's label it as figure 1. We can apply Schmidt's law for a situation in which the single crystal is at an orientation so that the slip plane is perpendicular to the applied tensor stress. Suppose the slip plane is perpendicular to the applied stress. The angle of twist is equal to 0, lambda is equal to 90 degree, cos lambda is equal to 0, therefore torque is equal to 0. As noted before, that angle do not always add up to 90 degrees. Even if the applied stress is enormous, no resolved shear stress develop along the slip direction and the dislocation cannot move, so that either lambda or the angle of twist is 90 degree.
For metals and alloys, electric currents may induce atomic diffusion and morphological changes known as the electromigration effect. Here, we report the first direct application of conventional solid mechanics theory to predict the electric current induced deformation based on the electron backscatter diffraction and synchrotron radiation based on X-ray diffraction analysis of copper strips under current stressing. At a given current density, the electric current induced elastic, slip, or slip accompanying with twinning deformation in copper strip was revealed. The Schmidt's law is well elucidating the occurrence of the electric current induced plastic deformation, namely the slip and twinning ones. The study unveils that electric current induced strain and deformation can be described in the same context as for the conventional solid mechanics. The present work demonstrates that the theory from conventional solid mechanics can be invoked to predict the electric current induced deformation. In situ EBSD reveals the electric current induced elastic, slip, or twin deformation transition when increasing the current density. The discovery conveys that electromigration effect is controlled by both the electrical and mechanical properties of materials. The EM effect have been highlighted as one of the most serious reliability issues in advanced integrated circuit, where the high current densities are applied on the fine conducting damascene or architecture. Typically, the EM effect involves the formation of voids and halogens at the cathode and anode of metallic lines respectively. In addition, it could also enhance or retard the reaction phase of growth at heterogeneous interface, namely the polarity effect. However, there are a number of non-directional electric current-induced phenomena reported in the literatures, such as non-polarity interfacial reaction, precipitation, crystallization, and recrystallization, which cannot be explained with a simple EM theory. More recently, due to the demand for high current density in new applications, more electric current-induced peculiar phenomena were reported, such as supersaturation and electro-recrystallization of plumbum and tin alloys, and non-directional formation of voids and halogens along the copper strip. A new theory beyond the ballistic model is needed for the EM effect. While many electric current-induced pulses are unsolved, implications for the correlation between the EM effect and the material's mechanical behaviors are seen in various experimental and computational works. For instance, film with 111 texture grain were found to be stronger EM resistant, while 111 plane is suggested to have the highest Young modulus. The nano-twin structure was found to delay EM effect, while this structure was suggested to have higher tensile strength.
The combination in copper strip under electric current stressing is identified to be the most dominant EM path, while it is known to be the slip system of copper as a phase center cubic or FCC metal. Copper is an ideal model material to answer this question because of its low stacking fault energy, and the deformation twins are prone to be formed under a tensile stress. A transition between the slip and twinning deformation exists, which depends on a critical strain hardening, strain rate, temperature, and grain size. In this study, the categorization based on scanning electron microscopy, or known as SEM, electron backscatter diffractometry, EBSD, and synchrotron radiation based SR-based were performed to study the morphological and crystallographic evaluation of copper strip under electric currents. The transition of electric current induced elastic slip accompanying with twinning deformation were revealed for the first time. The occurrence of the electric current-induced plastic deformation, namely the slip and twinning, was elaborated based on the Schmidt's law. A direct correlation between electric current-induced deformation and materials' mechanical properties is proposed.
That is all from me. Thank you.